In previous session, we have learned that the U00 function is the lowest order solution. We need to find more solutions to form a set of characteristic solutions. By finding out all the characteristic solutions, we can form an orthogonal set, and this orthogonal set can help us to expand any arbitrary input amplitude. And what will be all the characteristic solutions? They will be Hermite-Gaussians. Okay, that is, Hermite-Gaussians are the solutions of the Parallel wave equation. What are the Hermite-Gaussian functions? By the name here, Hermite-Gaussian functions means the combination of Gaussian function and the Hermite function. As we know, the Gaussian function has this form. And the Hermite-Gaussian are defined like this. The higher order Hermite function must satisfy this relationship. So from this relationship, you can find out any order of Hermite function. For example, by using this relationship, you can find out the third order Hermite function will be like this. Okay? Since we have learned the form of the Gaussian function and the Hermite function, what will be the Hermite-Gaussian function? We will have the 1D Hermite-Gaussian function. It can be expressed as this. So clearly, the Hermite-Gaussian function is formed by multiply Hermite function with the Gaussian function. And for 2D Hermite-Gaussian, it will have the form like this. It is the multiplication of two 1D Hermite-Gaussian. Okay, then let's go back to the U00 function. The U00 function can be expressed like this in the Hermite-Gaussian form. The U00 function means that it's zero order in the x0 direction and the zero order in the y0 direction. And the WOX and the WOY represent the minima beam radius along the x and the y direction respectively. C00 here is the corresponding factor. And then we can know that the UMN function can then be expressed as CMN, which is the factor, and along the x0 direction, the order of Hermite-Gaussian will be m. And along the y0 direction, the order will be n. This is the defined Hermite-Gaussians, and they are the characteristic solutions of the Parasian wave equation. So all the Hermite-Gaussian functions, they can form a set of the characteristic solutions. Since we have known the form of the Hermite-Gaussian, and we know the form of the solutions, what will be the Fourier transform of the Hermite-Gaussians? If you remember, I have told you that in chapter 6, we first find out the solutions of the characteristic equations, and they are the Hermite-Gaussians. And use these solutions, we can I should say that any arbitrary input amplitude U0 can be expressed as the superposition of these solutions. So any input amplitude can be expressed as the superposition of the Hermite-Gaussians. To find out the corresponding diffraction amplitude, we have to know the diffraction amplitude of these characteristic solutions. So that is why now we want to know the Fourier transform of these Hermite-Gaussians. We know that the Fourier transform of the Hermite-Gaussian will be as the following equation. The process of obtain this result is very complicated. So here I just provide you the final result shown here. And this is the Fourier transform of a Hermite-Gaussian. And as you can see, the Fourier transform of a Hermite-Gaussian is still a Hermite-Gaussian, right? This is because the Hermite-Gaussian is formed by Gaussian function, and if you have learned the Fourier transform, you will know that the Fourier transform of a Gaussian function is still a Gaussian function. That is why the Fourier transform of a Hermite-Gaussian is still a Hermite-Gaussian, but with the corresponding parameter shown here. Okay? If you want to plot the field distribution of the Hermite-Gaussian, I will show you some figures. For this one corresponds to U00. So along x and along y, you will have one peak. and this one corresponds to U10 function. Along x, you will have 2 peaks. Along y, you will have only 1 peak. And this one stands for U01. Along y, you will have 2 peaks. Along x, you will have 1 peak. And this one, of course, it will correspond to U11 function. Along x and along y, you will have 2 peaks. Besides, you can also plot the U function Hermit-Gaussian in this way. This one corresponds to U00 and U10, U20, right? For U20, you will have 3 peaks like this. And for this one is U50, you will have 6 peaks. And for this one is U11. So along x, along y, both direction will have 2 peaks. And for U33, you will have 4 peaks and 4 peaks along x and along y directions. Okay, so you should know how to plot the field distribution of the UMN Hermit-Gaussians.